Hello, welcome to the analysis of variance, sometimes called the ANOVA. This introduction is going to be broken down into three parts. In the first part, I'll simply be telling you what variance is, and then I'll be moving on to tell you what an important distribution known as the F distribution is, because it underlies much of the analysis of variance. In the second part, I'll be telling you what the analysis of variance actually does when it interprets data, and what the output of an analysis of variance in terms of the table looks like, and how to understand the various components in that table. And finally, I'll be reviewing what assumptions the analysis of variance makes when it tries to disentangle your data. Let's begin with the mean. We should all be familiar with the mean. It's simply the typical average. But at population level, we often give the mean a symbol with Greek letters, such as this mu. And at population level, if we had every single observation x in that population, the population mean is simply the sum of all those values of x, given by that sigma, divided by the total number of individuals in that population, which here I'm giving by capital N. So mu is the sum of observations divided by the total number of observations. Now, almost invariably, we don't know what that population mean is, but we typically have to estimate it. What we can do is estimate the sample mean, which is the sum of all the observations in the sample divided by the total number of observations in that sample, which is the sample mean. And here I'm giving it a Greek letter x, and the x bar is referring to the fact that it's the sample mean of all those values of x that are in the sample. Now, the good news is that the sample mean, if it's based on a random sample, is an unbiased estimator of the population mean. So if we want the best guess in terms of what the population mean is, we would typically use the sample mean. What about spread in the data, sometimes called dispersion? Here is a histogram of human body weight, where we can characterize the mean as somewhere around 150. But what about the spread around that 150? Well, perhaps the most important measure of spread in data, if we have at least the entire population at hand, is what we call the population variance. It's the average squared deviation of all the observations from their population mean. So there it's the formula. We typically give it a Greek letter if we are dealing with the entire population, and because it's a squared term, we will give it something like sigma squared. So it's the average squared deviation. Why do we use a square? Well, for one thing, it overrides this issue of positive and negative deviations from that sample mean. And secondly, it fits in very neatly to a whole range of other statistical theory which we'll move on to. So that's the population variance. But what would happen if we need to estimate that population variance from a sample? Could we simply use that same sort of formula as if we were dealing with the entire population and estimate it directly? Well, it turns out that we can't. We've got to use a slightly modified formula. Here I'm going to use the term S squared to represent the population variance as estimated from a sample. So it's not the true thing, it's an estimate of the population variance. And so I'm giving Roman numerals again. And here it's the sum of the squared deviations of observations from the sample mean, because of course that's all we've got to go on. But in this case, we're actually dividing by n minus 1 rather than n. And the proof isn't hard. It's based on expectation algebra, but it's been known for some time that if we want to estimate dispersion in a population as just from a sample, we can't simply measure that same index in a sample and assume that it reflects the same thing. We need to, in this case, divide by n minus 1. What about the standard deviation? Well, the standard deviation is effectively an attempt to undo the effect of squaring, but in this case we take the square root of the whole thing rather than just the numerator. So it's defined as the square root of the average squared deviation in terms of the population standard deviation. And likewise, if we're trying to estimate the population standard deviation from a sample, we take the square root of s squared, which is this formula down at the bottom. So let's revise. Typically, population parameters in most statistical texts will be given in Greek. These are things we do not know, things like the population mean or the population variance, the average squared variability, or the population standard deviation. We will estimate these from a sample, and the unbiased estimators can be termed with Roman numerals, and here we've got x bar, s squared, and s. I'll now move on to the second element of this first introduction to the analysis of variance and introduce this guy, Ronald Fisher, a really very important influence on modern statistics. He gave us the F distribution, named after him. He also gave us the analysis of variance. He gave us degrees of freedom, which we'll see, significance testing, and made many contributions to experimental design. And you can actually read some of his early papers where he first introduced the concepts of analysis of variance and indeed the analysis of covariance in the 1920s when he worked at an agricultural research station called Rothamsted in the UK. So what is the F distribution? Well, imagine that we've got a population of trees with normally distributed heights. So most of them are around, in this case, about 50. Some of them are a bit bigger, some of them are a bit smaller. But in this case, what we're going to do is have a thought experiment in which we go and repeatedly take two samples, sizes n1 and n2, and in each case work out the best estimate we can of the population variance, i.e. s1 squared and s2 squared, from those samples. Now it turns out clearly they are estimating the same thing, so you would expect them to be very similar. But by chance, one of those estimates can actually be higher than the other, or vice versa. So let that ratio, s1 squared to s2 squared, be f after Fisher. Clearly, as I've said, s1 squared and s2 squared estimate the same thing, so we expect that ratio f will sometimes be less than 1 and sometimes be more than 1. Imagine if we took two samples of size 5. Well, there is a theoretical distribution for the expected ratio of those two estimates of the variance based on those samples, and here it is. Some values will be less than 1, some will be more than 1, but by nature of the fact that it's a ratio, it will be constrained between 0 and infinity. So it's not going to be a symmetrical distribution, it'll actually be a rather skewed distribution. But of course, as we get higher and higher sample sizes, for example n1 is 20 and n2 is 20, then the expected ratio is likely to be much closer to the 1 than if we had a smaller sample size. So the variability in that overall F distribution is supposed to be less. Here is the defining attribute of an F distribution. If pairs of samples are repeatedly drawn from the same normally distributed population or two different normally distributed populations with the same variance, then that ratio will follow an F distribution. So what we need is a normal distribution and repeated samples from that ratio of s1 squared to s2 squared should follow a theoretical distribution known as the F distribution. Thank you for listening to this R-Labs tutorial video. If you found this useful, you might be interested in our free online Moodle course, or check out and subscribe to our YouTube channel.